I'm actually very excited because today is the day. Well, today is the day I'm gonna talk about something that really interesting and I really like. It's my favorite circuit. So bear with me. It's gonna be fun. I promise you, it's gonna be fun. So back at the very beginning, when I was talking about basic components, I'll be talking about resistors and capacitor and inductors and so on, and then I'll be talking about diodes and said that diodes, if we were having something like a normal circuit, like a DC circuit with a battery and then some kind of resistance and the diode polarized this way, then the current was going to try to flow through here and here and here and then get to the diode, but the diode was going to be polarized in the opposite direction of the current, so no current was going to occur. So there is no going to be current because the diode is not going to let anything go through it. So no, there is not going to be any current. But if the diode was actually going to be polarized in the opposite direction, so in this way, then it would let the current flow through. Now, we had to make a distinction between ideal diodes and real diode. Ideal diodes are gonna either stop or let the current flow through, no matter what. So even if I'm gonna have a huge spike in current and the diode is gonna face the opposite direction, it's gonna hold and it's not gonna let the current go through. But in the real world, if I do have a very huge spike of current, for a prolonged amount of time, so not for like milliseconds and so on, but for a lot of time, then the diode is gonna reach something that is called the breakdown of the of the diode, and so the diode is gonna literally break down, and then it's not gonna act like a diode anymore. It's basically gonna let all the even though it's facing the opposite side, it's gonna let all the current flow through, and even when you go back to your normal load, like with your normal current, the diode is gone. It's not gonna act like a diode anymore. So it's not gonna stop or let the current flow through. It's just not gonna do anything. It's just gonna be like it's not gonna do anything because it broke down. Then to solve this, there are some particular type of diodes which are called Zener diodes. Now, a Zener diode is basically like a normal diode, but when you're gonna have a huge spike, so a lot of current flowing through, and the diode is facing the opposite direction of the current, it's gonna say, okay, hold on, I'm not gonna be able to stop this. This is over my breakdown voltage, so I'm not gonna stop this. I'm just gonna let everything go through, and I'm gonna save myself by letting everything go through. So when the your huge prolonged spike is over, then the Zener diodes is gonna go back and say, okay, the huge spike is over. I'm gonna act again like a diode, and it's gonna survive. It's gonna act like a diode again. While a normal diode, once you get the huge spike, it's gonna try to act like a leader. So it's gonna try to be opposite to and oppose itself to the huge spike, and it's gonna die. So it's gonna literally break down. But on the Zener diode, who was been running away and then he came back to work again as a diode. So yeah, this is my very oversimplified explanation of what Zener diodes are. Now, The reason why I brought back diodes is not just to talk about, not just because of a recap or to introduce something like Zener diodes and so on, but I brought them back because back when I introduced them and the very first lectures, well, they're not lectures, they're videos on YouTube for like of me and some pieces of paper, but anyway, when I first introduced them and in one of the very first videos, I wasn't actually able to fully explain their potential. If you remember, I even said that they're very, very useful. Diodes are very, very useful, but I wasn't actually, able to tell you why they're very, very useful. But now that you don't only know about DC, but you also know about AC, I can tell you why they are so useful and widespread all over the place. Now, if you recall, when I be talking about AC, I said that the AC was going to be generated from a rotating magnet. This was going to induce currents, and then we have wires shifted 120 240 degrees one from the other, and the movement of the magnet was actually going to make three-phase alternating current, but then it was going to go through a transformer being brought up, carried through the wires up to the city, where there was going to be a step-down transformer, which was going to bring the voltage down, and then those three phases, only one phase was going to reach your household and therefore your apartment. So let's suppose that we indeed have only one phase. So a sinusoid of one single phase, oh, let me just use this, the blue pen, would look like this. Well, and then continue and so on. Now, this is the AC. Now, the problem with this is that although many appliances are gonna use AC, like your oven in your kitchen or something like your washing machine, other things like your hair dryer and so on, and basically everything that has an engine that rotates is gonna use AC. And like there are many things that use AC, like induction motors and so on. But everything that is digital, like your computer or your mobile phone, your tablet, your TV, literally anything, is going to use DC. So how do we get from monophase AC at either 50 or 60 hertz to DC? Well, if you recall, DC as opposite to AC in our graph will look something like this, like a straight line, and it's DC. How do we get from a sinusoid to a straight line? Well, we can use diodes. Why? Well, AC basically means in this monophase at either 50 or 60 hertz, basically means that electrons are going to flow in one direction and then in the other direction and in the other direction and so on 50 or 60 times per second. And this graph basically shows electron gaining velocity, then slowing down, stopping, changing direction, and then so on and so forth. While in DC, they just go through, like in this circuit, they just go well, in this circuit, if there was a diode like this, it will just go and flow from one way to the other, in this case from positive to negative, so in this way. Now, what happens if we use a diode? Well, if we have some kind of AC source and we use a diode like this, then we put something like a resistance and we are gonna measure what we get from A to B. This is my resistance, this is my diode, this is my AC source. Then what's gonna happen is that if I use colors and I say that current flowing to the right, this direction is gonna be green, and current flowing in the opposite direction is gonna be red. I'm just gonna use this kind of color coding. Yeah. Okay. Then if I do that, I'm gonna say, okay, fair enough. This one is gonna be the current flowing in this direction, and this one is gonna be the current flowing in the opposite direction. But then only the green one is gonna go through, because the red one will be blocked by the diode. So essentially, and over here as well, so essentially only just the current flowing in this direction is going to be led through, because the red one will try to flow, but it's going to meet the diode, and the diode is not going to let the current flow through. Therefore, it's not going to flow. And we're only going to have the green one. Now, if we were going to read the voltage across A and B, we would have something like, well, what do you think we're going to have? Well, we will basically have only this part. So we will have a sinusoid like this, and then like this, with nothing here, nothing in between, because if the current is alternating at 50 times per second, for instance, then we're only gonna let the half, well, only the half that is flowing in this direction go through, which essentially means that we're just gonna have 25, the current flowing for 25 times a second at the huge peak, and the huge peak, and then nothing here, like absolutely nothing half the time, which is not good. But with some kind of DC, I guess. If we were going to put a capacitor after this, okay, so this one plus a capacitor, we will get something that is still really pretty bad. Like, no, I'm not gonna say pretty bad, like really bad. It's gonna be attenuated a bit, but it's gonna be bad. Will be if we use a capacitor, we will have something like this, and then going down, then you spike again, then slightly going down, and so on. So yeah, this is better than this, but still, it's really crappy. It looks very far away from this. So yeah, some kind of appliances that require DC. Whenever you have an appliance that requires a DC, you need to use, well, like even for your phone and so on, you have a charger. That charger is actually just what it's doing is just trying to convert AC to DC. Now, if you purchase some crappy Chinese chargers, then they're gonna, well, I really hope not, but there is a chance that they might be using something really bad and really crappy like this. like this configuration plus a capacitor to get something like this, which is horrible, absolutely horrible, and even harmful for that matters to the internal circuitry of your mobile phone. So don't buy Chinese chargers. Now, what is actually used in real chargers, like the one that are generally sold together with mobile phones and so on, but also the one that are used for laptops and so on. It's not a single diode, a crappy single diode, but it's a full bridge rectifier. That's right, it's a full bridge rectifier, which I'm gonna show you, and is indeed my favorite circuit. So don't do this and don't buy those kind of crappy things, but always make sure that your charger has a full bridge rectifier in it. Now, what's a full bridge rectifier? Well, a full bridge rectifier is actually a circuit that looks like this. Let's suppose that we have an AC source, and this is gonna be my AC source. Well, my AC source is gonna be connected here, and we're basically gonna have 4 diodes. Not one crappy single diode and a capacitor, but 4 diodes and a capacitor. So, what I'm gonna have here then, it's a node, and here I'm gonna have a diode, and down here I'm gonna have another diode, like this. Then here I'm gonna go down and have this. I'm gonna have a switch which I can turn on or off, but this is just for explanation purposes. And then some kind of like a resistor, and I want to connect this to an LED, which stands for light. So this is an LED, which stands for light emitting diode. So an LED is essentially like something like this, which hopefully is gonna bright up. Then, sorry. Then here on the bottom, gonna have, well, I'm gonna connect to the ground just to be safe and correct. And then here on the other side of the switch, which I'm gonna call S, which stands for switch, I'm gonna have the capacitor. See, whoops. And now we go all the way to here, and then from here, what I'm basically, oh shoot, yeah, I can like this. Let me try to make it at the like not look too bad. So here I'm gonna have like kind of symmetrical. Here I'm gonna have another diode. Now we have 3 diodes, and now lastly I'm gonna have another diode here, like so. And from here I'm basically gonna go all the way down to meet my other wire, And from here, I'm gonna go all the way down back to the source. Okay, so let's do a bit of color coding, shall we? We said that this part of the sinusoid is going to be when the current is going to flow in this direction, and this other part is going to be when the current is going to flow in the opposite direction. So I'm going to say that the green one is going up and the red one is going down. Now, with the green one, what do you think is going to go? Well, let's follow the path. It's gonna go up and here and here and here. And again and again and again. Then it's gonna go down. And then it's gonna go down. Now we are at a node. Where do you think it's gonna go? Well, of course it's gonna go right. It can't go left because the diode is in the opposite direction. So it cannot flow in this direction, can only flow in this direction. So it's gonna turn right, and it's gonna go on and down and down. And here, well, it's basically gonna be the same. It cannot go in this direction, so on the left, because the diode is polarized in the opposite direction. Therefore, it's gonna go on the right, to the right. So going to the right, and going through my resistor, all the way down. Oh, there we go. We are basically reaching the LED. So this is fine. But so far, it will be exactly the same like our single diode configuration. So although the LED is gonna bright up, if we had only this one, so it will be like connecting it to this one. So LED, since they work in DC, but in this case we would have something like this, which will be a huge power, then zero, then huge, then zero, then huge. So our LED will light up and then go and then turn off, and then light up and then down, light down 25 times per second. So we wouldn't have an LED, we would have some kind of stroboscopic light. But we don't want to run a disco club, and we want just, a normal LED to work properly. So, sorry. But let's continue the path. Now, where do you think the... well, no, let's not continue the path. Let's see what the other part of the monophasic current of the sinusoid is going to do. Well, the one is going to go down, so let's follow it. It's going to go down, so it's going to go this way, and 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 then up. And then once it's up, it cannot go in this direction because there is this diode which is polarized in the opposite direction. Therefore, it has to go to the right. So here it goes to the right. Now this diode is gonna let the current flow through because it's polarized in the right direction. So the current is just gonna flow here, and here is gonna meet with this. Oh, and by the way, this is basically not. I have no way of animating this stuff, so I cannot actually show you how it's really gonna work. But since those two are are the same phase, but are the positive side and the negative side, so basically the one flowing in one direction and the other direction, when this current is here, this one is not going to be here. It's going to be only the green one. Then when the red one is here, the green one is not going to be here. So essentially they're not going to meet or overlap of any kind. This one is going to be here 25 times per second, and this other one is going to be here 25 times per second. So the other 25 times per second are gonna fill the gap of each other. So now the red one is gonna go through here, through my resistor, and yay, is going to the LED. So the LED is not gonna be a ultra stroboscopic light, like in a disco club, like we had for our single diode, so 25 times per second, but it's still going to be pretty, it's gonna be powered up 50 times per second. So it's gonna be pretty good. And down here, let's follow the path. Let's go back to our green one. Where do you think it's gonna go? Well, it's not gonna go to the ground, of course. It's gonna go back. It wants to go back to the power supply. So it's gonna go all the way to here, and here, and here, and here. Why don't we have copy and paste in real life? It would be so much easier. And then here, all the way to the top. Now, where do you think it's gonna go? Well, first of all, it's gonna go to up, and then it's gonna go here. The node is gonna go on this side, and it's gonna go here and here, and down here and down here and down here and down here, and again and again and again, and it's basically gonna go back to the source. Now, if we follow the other one, the red guy, well, the red guy is gonna go to the same path as the green one, but then it has to get and go back into the power supply in the opposite direction, because right now they're both in DC, they're not in AC anymore, but they have, since we need a closed loop in order to get current from DC, the current has to go back to AC in the right direction. So it's gonna go up and up again and up, but then once it gets here, it's gonna go up and up and up here and up here. Can I get this like up here and here and here and here and here and here and here, all the way back to the source. Now, we said that we're going this way with a full bridge rectifier. We're gonna use both the positive and negative, so both the current flowing in this direction and in the other direction. And our LED will not know that it used to be AC, because it's just gonna receive DC. But what is this current going to look like? Well, the DC current we're gonna have will be something like something like this. Which is okay-ish, because it's an LED, but it's not 100% right. Like, we can do better to get this line. So now let's suppose, and here we come to the reason why I put a fixture, a fake switch, let's say, because I do want this to all switch and turn it on every time. So let's suppose that I'm gonna close this switch like this, and now the current is gonna go through my capacitor. Now, how do you think it's gonna look like? Well, since we have a capacitor, we're no longer gonna have those, but we're gonna have something like this, which is kinda like a line, a straight line in DC. Full bridge, DC full plus capacitor. So these actually almost look like a straight line, because of the capacitor. So what do you think the capacitor is going to do? Well, the current is going to flow. It's going to be, is still alternating at 50 times per second, but now it's going to be direct, like so. But, if you remember, I said that the current was going to flow in this direction, then slow down, stop, 0, and then go to the other direction, then stop, slow down, stop, and go to the other direction. So this is essentially the current flowing, slowing down, 0, going to the other direction, and so on. So this is why we will still have those, kind of jumps. To get rid of those, we use a capacitor. A capacitor is basically gonna notice that when it's gonna be charged, and then it's gonna notice that for this, 50 times per second frequency, we're gonna have a gap in which the current is gonna slow down. It's gonna be less. So the capacitor is gonna say, okay, we have the LED. The LED wants power, so take it. Just I'm gonna discharge and give it to you. Then it's gonna be charged again, and it's gonna discharge, and gonna be charged again, and it's gonna discharge. Therefore, it's gonna attenuate and make those jumps as little as possible. So, you can play with capacitor in order to get this one resemble as much as possible to a really good flat line. And the more it resembles a flat line, the better. So this is actually how a full bridge rectifier works. And it's of course my favorite circuit above everything, because it uses diodes. It's one of my favorite circuits. It's probably my favorite circuit. It's very, very useful, and it's not complex. It puts together everything, AC and DC, and it's very, very widespread. I love it. I really love it, and I love the name of it. So let me just write down. This is a So a full bridge rectifier. There we go. A full bridge rectifier. So that's pretty much it. And now you can see why diodes are so useful. Then, oh, by the way, there is a reason why I connected the LED here and I didn't connect a light bulb. It would have been exactly the same. It would be totally fine for a light bulb to be powered up by DC, but light bulb can also work, the classic one with with tungsten inside and this thing. So light bulb can actually work both in AC and DC. It doesn't really make any difference. So you might think, okay, hold on a second, but you just said that if you're gonna plug AC, straight to a light bulb, then, well, I was talking about diodes, but essentially, if we were going to plug ACs, monophase AC alternating 50 times per second or 60 times per second for what matters, straight to a light bulb, then the current is going to change direction, it's going to be alternating. So light bulb will essentially, glow and go back and glow and go back and glow and go back and glow and go back. Then it wouldn't be fine, right? Well, no. As a matter of fact, light bulbs in our homes are actually connected to AC, but we don't notice it because there is the photo persistence of photons going to our eyes, and we're not gonna be able to notice it at such a high frequency. So either 50 or 60 times per second, doesn't matter, we're not gonna be able to notice it. However, if you use a very, very good camera, like a camera that is able to record at 200 fps, like 2000 frame per not 2000, sorry, just 200 frame per second, then you are definitely gonna see the light bulb going, glowing and then going dimmer and then glowing and then going a bit dimmer and so on and so forth, being like this, dimmer and dimmer and flow and glowing. Now, why do I keep saying flowing? Anyway, glowing and dimmer and glowing and dimmer. So yeah, that's why I didn't connect there a light bulb, because it would have been misleading, because otherwise it would have been that you would have been thinking, you would have thought that any light bulb in your house has a full bridge rectifier, but it's not true. It's the light bulb just run on AC. So yeah. Okay, so that's pretty much it. I hope it helps. So now you know what a full bridge rectifier is, and why it should be used as opposite to a single diode configuration, and hopefully your next chargers are gonna be made with a full bridge rectifier, and you're not gonna buy crappy, cheap Chinese chargers anymore. All right, bye, cheers, see you next time.